All right, I know folks are going to continue to trickle in from lunch for another few more minutes, but we have a lot of material to cover here today, so let's get started. This is session 3-334, .NET Framework Security. My name is Brian LaMacchia, and I'm the development lead for security in the .NET Framework. And what we're going to talk about today is an overview of the architecture and the key features of the .NET Framework security model. To do that, we're going to have to go through a number of steps and introduce some new concepts. We're going to begin with some discussion of the motivation and the design goals behind the framework security model. We're then going to spend a bunch of time talking about permission objects and walking the stack. You may have heard a little bit about permissions in some of the prior talks. They're our basic way of doing authorization checks. We're then going to go on and talk about what we call our evidence-based security model. That's basically a comprehensive term for our entire policy management system, which is really the key in any of these sorts of systems. Because when you're dealing with so many different types of code, coming from so many different types of locations, you have to be able to make reasonable determinations about what sorts of rights you want to give them. And that's what we'll go into in depth there. From that, I'll take you on not the magical mystery tour of the frameworks talk last time, but a very quick tour of the security classes and just what to go look for in the system.security namespace. And then we're going to shift gears for about the last 10 minutes of the talk, because I want to start talking about how you digitally sign XML objects. Some of you who are familiar with digital signature technology, in particular that stuff that comes out of Secure Mail, S/MIME v3, and CMS, know that it's not particularly well suited to the XML environment. So for the past year, there's been a working group, both in the IETF and the Web Consortium, that has worked on a standard for digitally signing XML objects and giving you XML back. We've been active participants in that working group, and I'm pleased to announce our support for that standard in the .NET frameworks, and I'll walk you through a demo of the code and also what a signed XML object looks like. So let's dive in. Why should you care about platform security? Besides the fact that you have an hour to kill and you're here in this room, why should you actually care? Well, I was trying to come up with motivation for this, and it was early May, and I walk into my office and I fire up Outlook, which is one of my favorite mail programs. And of course, my Outlook screen looks like that, right? And that probably happened to you too. And at first, you feel really good that all these people on the internet are sending you messages of love. I mean, we work in dusty offices that are alone, and all these people say they love me, and then I have to go delete 1,000 mail messages. I want to focus on the I love you virus for a second, because I want to talk about exactly what happened there, because it is representative of one of the key scenarios that we're trying to solve in the .NET framework system. We have a host program that runs locally, in this case Outlook. It happens to expose some resources that we want to make available to good mobile code. In this case, well-behaved mobile code. Things like the Outlook address book. Things like the ability to send mail on behalf of a user. These are things that you want to be able to work with other sorts of non-malicious programs like synchronization software for your PDA, stuff like that. We then downloaded some content from the internet in general, in this case a mail message, that had some active content as part of it. We went and ran that active content, and it turned out to be malicious, and it used all those nice features that we were so nicely making available, and it did bad stuff. That's the sort of thing that we want to try and protect ourselves against. Now, the key there is that we really have to do two things. We have to put security checks in the resources that we expose to code that might be malicious. And then we have to be able to identify the code that might be malicious and give it a restricted set of access rights. So there's two parts to this. You can't just universally say, as long as I know that the code is bad, I can protect. I have to be working hand in hand with the security system. Now, there are all alternative approaches to this model. One of them is the traditional sandbox model, where you create a protected environment and you don't care what the code can do because it can't harm anything. And that's great if you want to put dancing hippos up on the screen or something like that. But if you want to do some useful work, usually that's not sufficient. You have to be able to interact with other resources. The alternative approach is to fully identify, say, the entity that created the code, so that if it does anything bad, you can go sue them later. And that works in certain environments as well, but isn't really well suited to the general mix and match of components on the internet. So that's the sort of thing that we're trying to do. We're trying to draw the line and work somewhere in the middle. So our primary design goal is to provide a robust security system for partially trusted mobile code. That is code that's going to fall somewhere between that spectrum of no rights and full access with all the rights the user has to the system. We're trying to distinguish between different pieces of code that are still running in the same user process and have the same user identity. Now, we have to do a couple of other things to make this system useful. First, we have to make it easy to express fine-grained authorizations. That is, it has to be real easy to say things like, this particular piece of code has read access to /temp on my C drive, or finer-grained even than that. If I can't do that, I can't hand out fine-grained authorizations and segment code the way I want to. I also have to make it very easy to extend and customize the system. Why? Because you developers out there are going to want to build your own resources, protect your own resources, and you're going to devise your own permissions for the system. You're also going to want to integrate your own business logic into the policy system. And if I don't give you enough hooks, and if there aren't enough ways to customize the system, tailor it to your particular application's needs, then the security system hasn't met your needs, it's not useful. Finally, we have to make it very easy to perform security checks from user code. And this is a big point, too. Unfortunately, one of the typical design patterns when you're rapidly trying to develop an application is to make it work first, and then I'll make it secure later, and I'll go back and put the security on top. And we've found time and again that that's not a good approach to doing things. But if the security system is very burdensome to use strictly from the point of authoring classes, then there's a disincentive to do the work at design time when the architecture of the thing you're building is fresh in your mind. So we got to make it easy. Now, there's a fourth design point that I want to mention here that won't really be talked about elsewhere in the talk, and that's a design goal of having no end-user UI. By that, I mean I never want an application or the security system in the process of running to the end user to throw up a security dialog. Why? Because the user doesn't really know what to do with that dialog, and they are now conditioned to just swat the dialog box away and say, okay. Right? We see this time and again, and if I throw up a dialog box in the middle of downloading a control that says, well, this particular piece of code from this guy wants to have write access to your Windows directory. Yes or no? Well, what do? How do you have enough information at that point to even know why it's asking that question? So in this system, the policy is defined ahead of time, and you are either granted or refused rights based on that policy, but we will not prompt the user by default for anything in the middle of execution. You could always choose to do so in your own applications if you wanted to. Okay, so with that motivation in mind, let's go on and talk about how we do authorization checks. And for that, let's first get a couple of definitions fixed. Two primary things in security that go hand in hand: authentication and authorization. Authentication is the process of determining who or what is asking to take a potentially dangerous action. You know this from when you log on to an NT system. It's doing a query for you to prove that you are associated with a user identity that NT knows. And then there's the authorization half, which is, okay, given that I know that it's Fred logged onto the machine, is Fred allowed to write to this directory? Okay. This talk's going to focus on authorizations. We're not really going to talk about user authentication, although the ASP Plus security talk, which is the other session listed there, talks a lot about the user authentication models and how they fit in the ASP Plus framework. We're much more interested in how we do the authorizations. Once we have identified the piece of code that has come onto the system, how do we decide what rights it should have? Okay, first definition of a permission. A permission object, and it's just a standard object in the system, represents a specific authorization. For example, read access to that temp directory on my C drive. We do two primary things with a permission. We grant them and we demand them. The policy system grants authorizations, grants permission objects to assemblies. And our basic unit of grant is an assembly. When we load an assembly into the common language runtime, that all of the modules, all of the methods in that assembly will get the same grant of security rights. Now, again, if I grant something, I better go check for it somewhere. Otherwise, well, why'd I go through the grant and what am I protecting? So when in my classes, when I do a demand, that's a security check for the corresponding grant. And when I demand a particular permission object, I am requesting whether my caller, and in the general case, all the callers up the call stack, have a permission grant that encompasses the thing I demand. It may be larger than what I'm demanding, but I want to make sure that whatever I demand is completely contained in everybody's grants. Now, the frameworks includes a rich set of permissions that mirrors the set of resources that we expose through the frameworks. For example, we have something called a file I/O permission, and that's a permission object that represents read, write, execute, delete, create types of access to file objects in the file system. And our frameworks classes, when you try and create a file object or a file stream, will demand the appropriate permission for the operation you're attempting to do. We have things like socket permission, which relates to low-level network access. UI permission, which gets used by the WinForms classes to display windows on the screen. And there's different gradations of UI permission, from no UI to take a complete control of the screen to create sort of safe sub-windows that are appropriately decorated as coming from the runtime. That also controls clipboard access, and there's gradations of clipboard access. We also have permissions that relate to users and user identity, such as the principal permission, which relates to the identity of the user that's running on the current thread. Now, all you have to do to implement a permission is meet a particular interface, iPermission. And that defines basic set operations for comparing two permissions, union, intersection, subset, etc. But there's a further classification of permissions, what we call code access permissions, that have a particular behavior in how they do demands. And when they do a demand, they look at all their callers on the stack. They do a stack walk, and they're checking that everybody above the demanding frame has a particular permission. And the reason for this is very simple. We're trying to protect against repurposing various components in the system. You're going to be mixing and matching components from lots of different locations. They're going to have different rights. You may choose to give a component from company A read access to your file system, but not a component from company B. And we don't want B to be able to indirect through A to access something if it wouldn't normally have those rights. So that's why we're trying to prevent against luring attacks. And that's exactly why we do stack walks every time we do a demand for a code access permission. Now, the other thing code access permissions have to have that we'll talk about in a minute are some support for what we call dynamic stack modifiers. We also give you very fine-grained control of modifying the behavior of that stack walk, which you have to do in certain security cases when you're writing basically what we call gateway classes between different security environments. We also make it very easy to make these checks, and we do that in two different ways. First, you can make imperative security checks. That is, in the method implementation itself, you can create an object and run demands. The second option we have that is also useful is to make security checks declaratively using the custom attributes power of the metadata. And I'll show you how to do that in a minute. But let's first talk about what a stack walk is. So here on the screen, we have a sample application domain represented by the white box with 4 frames on the stack that come from 4 different assemblies, and they're A1 through A4. My call stack grows down, so A1, the method in A1 called the method in A2, called A3, called the method in A4. Associated with each of those assemblies is a set of granted permissions, and it is different on an assembly-by-assembly basis, or at least it may be different, depending on your particular policy. Each assembly has a corresponding grant set. Now, when that method in A3 calls that method in A4, that method in A4 is a protected method, and it requires certain security rights in order to call it and implement its function. In particular, it requires that all of its callers have permission P in order for it to then continue to execute. So what happens is we compare P moving up the stack frame by frame with the grants associated with each frame on the stack. So first we'll compare the permission P to the overall grant set G3. If P is contained in G3, if the grant set is larger than the demand set, then we continue. If not, we immediately throw a security exception, and processing will halt in that method, and it will be caught somewhere. We then continue up the stack, assuming it passes, testing G2, then testing G1. Pretty familiar. Now, let's say that you're writing a wrapper for an unmanaged resource. We do this in our frameworks all the time. And let's say you have some other unmanaged code, say some native COM classes or something, that you want to expose through a restricted managed interface for other folks to use. Well, in order to do that, to make that call to unmanaged code, there's a particular security permission that you have to have. It's called the right to call unmanaged code. Actually, it's called security permission unmanaged code access or something like that. But basically, it's a very tightly controlled permission, because once you call unmanaged code, you are stepping outside the bounds of the security system. So you certainly don't want to hand that out to everyone. You want to audit where you hand that out. But that means that if you did a stack walk for a piece of code that did interop to go call an unmanaged class, that it would fail because the stuff above it probably wouldn't have that right. So what you have to do is you have to have a way of saying, I'm willing to take responsibility for my callers. And that's what we call an assert. And so for any permission object that's a code access permission, there is this ability to say, I'm willing to take responsibility for my callers having this permission. Now, you have to have a special right to even do this, but this is the way in which you transition between different security contexts. And the most common design pattern, if you're writing a wrapper for an unmanaged resource, is to demand an appropriate permission from your callers, such as a file permission if you're doing something with the file system. Then you turn around and assert the right to call unmanaged code, which you must have been granted yourself. Then you make the unmanaged call. So we give you some very fine-grained dynamic control over the stack. And there's other modifiers that allow you to do things like temporarily remove some permissions you're granted. If you're calling a piece of code you don't particularly trust, you can mask out some of your own permissions, or you can give the code you're calling a restricted subset of what you currently have on the stack. So how do you actually make a security check? Well, again, there's two ways to do it, and it's pretty simple. This example was pulled directly from the implementation of our actual file classes. I just cut and copied the code. This is our file constructor, and you pass in the string for the file name of the representing the file you want to represent in your object. And let's say that, and it requires read access. So you can't even construct the file object representing temp foo.txt unless you have read access to that file. So what do we do in the constructor? Well, the first thing we do is we have to fully qualify the path name, because our permissions always act on fully qualified names. It doesn't make sense to say you are allowed or denied access to foo.txt wherever it appears in the file system without context around it. And then what we do is very simple. We create a file IO permission object, and here it takes two arguments. The type of access you want, that's a file IO permission access.read. That's an enum, file IO permission access. And then we pass in the path that you want, and then we call demand on it. And what that does is that goes and triggers a stack walk. And it goes all the way up the stack and makes sure that all the callers above have read access to the file you've asked for. If that succeeds, then we just continue on with the rest of the function, and there's no side effect. If that security check fails, this method will generate a security exception, and it will be caught wherever the first and closing catch block is above it. Now, that's all well and good. But you can also do security checks in a second mechanism that has some other nice properties. And you can do it declaratively. That is, it's possible to actually use the custom attributes on any particular method to make a security declaration. In particular, here's a method called foo that requires that you have write access to /temp in a file IO permission before you can call it. Now, you're not writing an implementation there. You're writing an annotation on the method that says to call this method, any caller has to have write access to /temp. And what happens is that gets carried along with the method as a custom attribute in metadata. When this method is JITted, just-in-time compiled, that security attribute declaration gets converted automatically into a security check. And then every time you call the method, it goes through and it will trigger that check first before calling the implementation. Now, that first off happens to call out the security right at the top of a method, so you can easily see what's required. Has an additional benefit, which is that these attributes can also attach to classes. So you can attach a demand to a class, and what happens is it applies to all of the methods inside it unless overridden individually. And there's also a couple of other types of demands that are weaker than demand that you can use. For example, you can do an inheritance check to check subclassing rights, or a link load time check to check that your caller who linked to you has certain rights. And those are also done through declarative security. That's basically all it is to walking the stack and doing permission checks. We're just doing subsetting operations among these types of objects. Now let's go on and talk about how we actually grant them, because that's the really interesting thing, is how do we decide what rights any individual assembly should have in the system. We call this evidence-based security, and there's basically three fundamental types of objects in the system. We've already talked about the permissions that represent the authorizations. Then we have policy. Policy is the process of determining what set of permissions to give to an assembly. And policy depends upon what we call evidence, which is the collected set of inputs to the policy, and it can come from any number of sources on input to the policy system. All of these are extensible and customizable. You can define your own elements of the policy system. You can define your own types of evidence, and this is useful in particular scenarios. And of course, you can define your own custom permissions that work with the standard policy system. So policy is obviously the process of determining permissions granted to code. And again, one of the key features here is that the permissions are associated with the identity of the assembly, not the identity of the user. We're trying to get a finer grain than simply user isolation and rights assigned to a particular user. So when an assembly gets loaded, we look at the identity properties of that assembly that is captured in the evidence, and then we assign rights on that basis. Now, by default, in the bits you have, there are two levels of policy that are in the system. There's a machine-wide policy and a per-user policy. As the standard, the user policy can make further refinements on the machine-wide policy, but it can't override the machine grant. And we have basically levels of policy levels for a machine and for user, and it is actually possible on a per-application domain basis to create a restricted subset even of that. One of the hardest things about policy is trying to draw the right boundary between how flexible do I make it and how easy is it to analyze. You make something too flexible, it becomes very hard to analyze, and you run the risk of making a small change in policy and having it have a cascade effect. On the other hand, if you make the policy too inflexible, it doesn't serve to meet your needs. We think we've hit the right balance between those two in this system. So we've modeled the system on a group concept, except we're grouping code and code identity as opposed to users. So each policy level is a hierarchical collection of code groups. And since code has identity in the runtime, just like users have identity in NT, we can group code together into groups, well, code groups of code that are related and have similar properties, and then we associate permissions with each code group. We test for membership in these groups by looking at the evidence that comes in with the assembly. And the basic rule is if you're in the group, then you get the permissions that are associated with the group. So what are some of the things that we can ask and that we can make group determinations on? On the bottom half of the slide, you see a typical hierarchy. By convention, the root of that tree is always a group called the all code group that matches every piece of code that comes into the system and in general has no permissions assigned to it. We can then do tests based on properties of the assembly. For example, we can ask whether the assembly was authenticode signed by Microsoft and has a trusted chain of certificates that goes up to a valid root for authenticode. And if so, that proves the assembly matches the publisher authenticode group. We can ask whether the assembly came from a particular zone on the internet, local internet, leveraging the IE zones model of security. And if so, we can grant it certain rights. We can ask whether the assembly was downloaded from a particular site. Now, that's obviously less secure than a cryptographic sort of piece of information, but for some scenarios, that's sufficient. And we can ask, well, did it come from xyz.com? And we can make determinations based on that. We can also make determinations based on shared name. You've heard about shared name in some of our deployment stuff, and it's a cryptographically sealed namespace that is controlled by the developer or a group of developers. So we can say, did this piece of code happen to come from, not only was it published by Microsoft, but was it also named ms.office? And if so, then it gets certain rights. Or we can ask if it was published by, a corporate admin or comes from the local web. Now, one of the things about these groups are they basically have two parts. They have a function that determines whether or not you're a member of it. That's the thing that looks at the evidence, and it gives you back a thumbs up or a thumbs down. Is it in the group? Is it not in the group? It's a Boolean function. If the evidence proves you're a member of the group, then first, we'll consider whether you're a member of that group's children, and then second, you'll get the rights associated with that group. If you're not a member of the group, then we'll never look at the children. If you're not a member of the publisher Microsoft group, we'll never ask if your name is MS Money, for example, in this new one. So let's walk through how this sort of works. So here's a sample policy level, again from the last slide. And let's say that I am running MS Money. It's been shared name signed MS Money, and I'm running it off my local intranet. And I've loaded up into the system, and I've pulled this assembly in. What rights does that assembly have? Well, I start at the top of the tree, and I walk down the tree. And of course, I'm a member of the all code group, so that test passed, and I would get whatever bucket of rights are in P1. I then look at the children of all code, and this assembly was published by Microsoft, so I have a piece of evidence that I've cryptographically validated that says so, and I can show that that piece of code is in that group, and I'll get the rights in P2. Now I look at that group's children. It's not named MS Office, but it's named MS Money, and that validates. So I'm in that group as well, and I get the rights in P7. It didn't come from the internet zone. It came from the local intranet zone. Doesn't match either of the children, and it didn't come from xyz.com. So having propagated through the tree, we've determined the set of rights that this policy level says this assembly should have, and it's the union of P1, P2, P7, and P4. Now that's one particular policy level, say the machine level or the user level. You have the ability to actually have different configurations at each level, and then we'll look at the intersection to make sure that you're not trying to exceed the rights one level grants over the other. This is completely configurable. We give you a pretty good default that's based on zones to start. But if you wanted to add a particular group at any point in the tree to represent code that was signed by your IT department, for example, or published by a particular publisher, or strong name signed, you can plug that in and work with it. And of course, you can also define your own functions for making your own determinations based on whatever it is that you want. Now, the input to policy is what we call evidence. And evidence can, in fact, be any object, although it is typically information about a code assembly. There's some stuff that you get by default. You get information about the cryptographic attributes of the assembly. Does it have a cryptographically sealed shared name? Does it have an authenticated publisher? We also get information about where did it come from. What URL did it come from? What zone? What site? These sorts of things become pieces of evidence that an individual policy group is free to look at or ignore as it sees fit. And it can make a determination based on those, or a determination based on a group of them. Our policy objects that we ship in the system pretty much look at exactly one piece of evidence at a time. A zone group will look at for a piece of zone evidence. A shared name group will look for a piece of shared name evidence. But you can construct group types that actually look at multiple things. So you can look, for example, to see if an assembly was signed by two independent authorities. Or you can see if you downloaded from some location and it had some other right. You could also do that by nesting groups, but you may want to do it in one. Any object can be a piece of evidence, but understand that there's a pitcher and catcher relationship here. A piece of evidence is only going to be meaningful to the policy if there's something over in the policy that's looking for it and changes behavior because of it. So just because you throw some evidence in doesn't mean it's going to modify your policy system. Or just because you respect something new doesn't mean that you're actually going to see any impact on your security policy. Now, how do hosts and applications have input and influence on the policy? Well, first off, the host gets to specify some evidence when it loads an assembly and gives it to the runtime. We call this implicitly trusted evidence, and the reason's real simple. If the host is lying to us, we can't tell. And we assume that the host that spins us up is going to be truthful. If it says this assembly came from xyz.com, then we believe it came from xyz.com. The host, in some sense, is outside the boundaries of the security environment, and it's impossible for us to make a separate determination. There are some things we could tell on our own. If you had a third-party piece of evidence that was cryptographically signed, you'd go validate that internally. But there's some things that we just can't tell inside the security system, and we depend on the host to give us valid information about it. Now, it's also possible, as part of the way that hosts can influence policy, is you could have custom membership conditions, that is those Boolean checks on a group, that tie into your legacy authorization system. So let's say you have a huge database already of authorizations that you want to reflect in our system. Well, you don't have to throw that out. What you basically do is write some interface code, some glue, that uses evidence that comes in and some custom code to go out and query your existing authorization system, read the rights back, and then represent it back to us in some permission object that we can then test for. Let me give you an example of another scenario in which it's useful for hosts to be able to influence policy and pass some custom evidence in. Let's say that you're an ISP and you want to do ASP Plus application hosting for like 1,000 virtual domains. And what you do is you sell service to the various people who own those domains and you give them different rights based on how much they're willing to pay. So you sell them a gold level of service and they get to write 5 megabytes of state to the disk. And if you sell them silver and bronze, they maybe get to write only a little bit or not at all. So you want to give gradations of rights. You don't want to have to administer separate rights for every virtual domain. What you want to do is simply qualify and say, what type of customer are they, and then have that automatically map to a particular bucket of rights. And you do that basically by passing in a piece of evidence that says, this assembly came from this type of customer, and you configure the code group so that that piece of evidence triggers off a different bucket of permissions. It's really pretty simple. Now, it's also possible for application domains to limit the policy of other domains they create. So that is, if you create the equivalent of a sub-process, you can control the policy and restrict it beyond your own rights. As an example of this, tomorrow there's a talk on SQL Server and .NET integration. And one of the things they'll talk about during SQL Server is their plans to use user-defined assemblies for custom functions in SQL stuff, SQL expressions. And those user-defined assemblies get loaded by SQL into a restricted domain and get run with restricted rights. And of course, the rights that are assigned to an assembly depend upon the configuration of the SQL Server and what rights you want to give to that custom code. Okay, so that's how hosts have influence on policy. Now let's talk about how assemblies have input to policy. And assemblies impact policy in two fundamentally different ways. First, there's a handshake between the assembly and the loader where the assembly gets to request certain rights from the system. And you saw Jim Miller talk about this briefly yesterday in the overview talk. There's 3 types of permission requests that an assembly can include inside it. It's completely optional to do this, but it gives the security system a lot more information about what you need. And it can tell you right off if you're not going to get it. So the first off, there's the set of minimal requests. Those are the set of permissions that your assembly has to have in order to function. You define those. Basically, if you have to have write access to /temp, and you're not going to get that from the policy system, you want to know it up front. And if you put that in a minimal request and the policy system refuses to grant it to you, we will refuse to load you. It's that simple. You put whatever you can put and make the minimal set as large or as small as you want, but we will not load you if we're not willing to grant you all of the rights in that minimal set. Now, obviously, you may also want to have conditioned execution where you add more features and enable more features based on what rights you have. And that's where the optional set comes in. And it works exactly like it sounds. Rights that you specify in the optional set are things that you are requesting, but you may or may not be granted. And you can test for that after you're loaded. And if we refuse to give you something in the optional set, we're still going to continue to load you and start you up. The final set is called the refuse set. And this is the ability for an assembly to say, under no circumstances do I want to receive a particular right. And this is basically based on, the principle of least privilege. If I know that I, in my assembly, am never going to do file access, then I never want to get file access. I never want to be granted that right. Because I don't want to be repurposed accidentally, no matter how much, if I don't want there to be a bug in my software that would allow some piece of malicious code to repurpose me and my rights to do something on its behalf. So you can specify there any set of rights that you absolutely don't want to be granted. And of course, what happens is the assembly, we compute what's called the max allowed set, which is the maximum set of permissions that policy is willing to grant to that assembly. And then we intersect it with the union of the minimum and the optional set. And then we subtract off all the refuse stuff. And what remains is the grant set for that assembly. And so once you have your policy set, you can figure out exactly what rights you're going to get. and you can control what minimum sets you need and what you don't want. Now, there's another really interesting feature of assemblies. Oh, I guess let me jump back for just a second. The way you do those requests is you use the custom attributes on an assembly. So you use the same sort of syntax that we used for a metadata demand, except you actually say that you're requesting minimum or requesting optional or requesting refuse. So it's the same sort of syntax, and it just happens right there in the source. But now assemblies have another feature, which is that an assembly can carry a piece of evidence along with it as well. This evidence that comes from an assembly is what we call initially untrusted. It's not trustworthy. It's coming from a source we don't know. Policy may choose to look at that evidence or completely ignore it. The case where it's really useful is when you do things like third-party certifications. So let's say that you're a software developer and you're going to develop a library that you want to allow other people to buy rights to call, but that library is going to be widely distributed. You can actually hand out to the people who license your library some sort of digital signed statement that says, this third-party developer is licensed to call this piece of code, and then you set up policy so that you can only call into your library if they have that right. So you can do all sorts of third-party certifications where like a certificate or something like that is carried along with the assembly from a trusted third party to prove that the assembly should be allowed to do something. Well, you have no reason to, for example, you have no reason to trust an assembly that comes from site A, but it has a signed statement from, say, an antivirus scanner that says that it's okay, even on top of our security system. Okay, so let's just walk through how this all fits together. So here we have on the screen an application domain with two assemblies loaded into it, A1 and A2. Again, the call stack rows down. Grants associated with it. We have our policy evaluator. That's the big purple thing on the right. And then we have the host and the security policy. So A2 decides it wants to call a method in assembly A3. What happens first is we have to go load that assembly. So we go locate it, and we find out where A3 is. And during the load process, what we do is we extract the evidence. We extract the implicitly trusted evidence from the host, and the initially untrusted evidence from the assembly, and we bind this up into an evidence object. That evidence object gets combined with the permission requests from the assembly and the security policy in that policy evaluator we just walked through. Policy evaluator grinds, spits out a grant set G3, which are the set of permissions that are granted to the assembly. We load the assembly in, method gets on the call stack, and we associate that set of grants with the method. And that's basically how it all works together inside of the system. Okay, now I want to move on and take you through on a quick tour of the security classes and give you basically some hints as to what you'll find in the various namespaces. The one you're probably most interested in, and the one you'll probably look at first in our bits, is the permissions namespace, system.security.permissions. This is the namespace where all of our permissions live, and we have both our individual permission classes as well as the various declarative permission attributes that you can use in the metadata syntax. If you look at the declarative attributes, there's one per permission, there's one mandatory argument, which is the type of demand you're doing, and then you'll find optional properties that you set based on the type of security demand you want. So that's probably the first place you want to go look. Another namespace that I didn't get to mention except here in this talk is isolated storage. And you'll find this actually under system.io. Isolated storage is a feature of the runtime that allows you to persist data on an assembly or application-specific identity basis over time. So if you think about what a cookie does inside the browser, the cookie gives a site a way to store some data on the client machine. Isolated storage gives an assembly or an application a mechanism for storing data on the machine that only it has access to. And that access is mediated by the system. Now, you have to have a permission grant in order to even use the isolated storage feature. And part of it is a quota as to how much space you get to store. But if you wanted to allow a shared component to persist some state without giving it access to the registry or to the file system, we have this secured resource that you can use. And basically, there are two classes that you care about there. There's the isolated storage file class, which is mirror image to the file class. It's a file abstraction within the isolated storage store. And then there's also isolated storage file stream, which gives you a data stream into a particular file. Now, there are 2 sample applications showing how to use isolated storage on the CD. And I don't know if it's on the CDs you have or the one that you get afterwards with the session-specific information. But you'll find under the directory for this session two example pieces of code, just called ISO storage 1 and 2. And they show you how to do assembly-specific storage and application-specific storage. And you can play around with those. Now we have the 3 other sets of classes, 3 other namespaces. We have our root namespace, system.security, which mostly contains infrastructure classes in them. The thing that is probably of most interest there is our permission set class, which is a way to group together individual permissions. It's a set, it's a collection object that allows you to have one instance of each type of permission. So you can stick a file I/O permission and a socket permission in there. But you can't stick 2 file I/O permissions. You'd union them together first and put it into the set. And then you can do operations on a permission set, just like you do operations on an individual permission. In particular, you can demand a permission set. And what that does is a stack walk that in parallel demands all of the permissions inside it. And you can union permission sets that does type-by-type union, take intersections, etc. And that's a nice way to collect together a bunch of operations if you want to check for multiple permissions in parallel. In the policy namespace, that has all of our objects for the policy subsystem. If you want to implement custom code groups, there's an iCode group interface there that you need to go implement, and there's an iMembership condition, which is the interface on the Boolean function that takes in evidence and gives you back group membership. There's also a namespace, system security principal, which has some roles-based security-related objects for dealing with like the principal permission and the role and the individual roles that are represented on a thread. Now I'm going to talk a bit about our cryptography classes, which also fall into the same domain. System security cryptography star is where we have our core crypto classes that basically are a managed representation of the cryptography APIs that are available, the core crypto APIs that are available under Crypto API. Those of you who have used Crypto API know that it's a very rich API and not necessarily the easiest API to use. We've layered a managed wrapper on top of it so that you can access algorithms in an easier fashion. What we've done is define an abstraction for each basic type of algorithm, symmetric algorithm, triple DES, DES, RC2, etc. Asymmetric algorithms for RSA, DSA, hash functions, signature formatters like PKCS1, etc. And those classes are all there. Underneath each type abstraction, we have a particular abstract class for an implementation. So there is an abstract triple DES class, and then we have an implementation class that glues in underneath, that which in our case maps to an implementation in Crypto API. So it's possible in the purely managed world to do data encryption and decryption, raw digital signatures and signature verification, all from the managed world without going out through pinvoke to go to native Crypto API. There was a demo of this, unfortunately, in a talk that was in the last hour, in the Handling the Basics Infrastructure session talk. But if you go get the slides there, you can see the demo code for how to do very simple encryption using, I believe, DES or triple DES. Okay, so now for the remainder of the time, I want to move on and talk about digitally signing XML objects. As you have probably guessed, Microsoft is very seriously committed, to using XML, and we see a lot of uses for it. One of the problems with XML currently is that there's no way to do integrity protection on an individual XML object. Yes, you could wrap it up inside a signed mail message, or you could PGP encrypt a piece of XML, or you could send it over a secure channel. What you really want is a way in which to take an XML object, digitally sign it, and get back an XML object. So there's a standards group that's been working on this that we have been participating in for the last year. That's joint between the IETF and the World Wide Web Consortium. And it's called XML DSIG. And that standard's now in last call. It's about to be to become a proposed standard or a recommendation in the W3C nomenclature. We have classes under System Security Cryptography XML that are in the bits that you have that have our first implementation of this digitally signed XML standard. Basically, it's pretty easy to use. We have a high-level signed XML class, which I'm going to demo in a minute. And then we have a bunch of lower-level object classes that represent the components of a signature in the XML namespace. So there's a signature tag and there's a signed info tag. And we'll see how these go together in a minute. And we have basic objects that you can create and put together just like you would create for the if you were implementing the standard on your own. So XML DSIG differs from some of the other signature standards that you might have played with before, in particular CMS for SMIME version 3, in that it provides 3 fundamentally different ways to sign an object. And you're going to use one or the other depending on what matters best in your particular situation. We call them wrapped, embedded, and detached. Wrapping works like cryptographic message syntax, CMS, in that you wrap the digital signature around the object. The object is embedded inside the larger signature blob. Embedded is the opposite. Embedded, you sign the object, and then you create the signature independent, and then you stuff the signature into the object. And of course, when you hash the object to verify, you have to skip over the signature that you just insert into it. But the advantage of embedded is that you don't fundamentally change the top-level structure of your XML document just to sign it. When you wrap, you lose the top-level namespace, and instead of having, say, a Word doc identified in XML, you now have the signature thing you have to know first. If you use embedded, you can skip over it later on down. The third mechanism is detached, where we do a pure signature on an object that's remote, and the signature and the signed object are not related except by a hashed reference. So you can take an object out on a web page, and any number of people can create a signature for it that sits somewhere else. Another point about XML DSIG is that it's key-centric. You're not required to go get any certificates in order to sign something. You can certainly do so if you want, but you're not required to do that, because based on your particular environment, you may know the party you're communicating with. You may exchange keys out of band. You may have an a priori trust relationship set up. So we don't require in the standard that you go out and get public certificates and expose all the information that's in a certificate every time you send create a signed message. Now for the demo, let's say we want to sign this little element that's my element and it contains my data inside it, sort of a little trivial piece of XML. Let's first look at how you construct the signature operation for signing XML. And so what we're going to do is we're going to author the sign method right here. That sign method has to take 2 arguments. It takes the key, the asymmetric algorithm key that you want to sign with, and it takes the element, the XML element, that you want to be the object of the signature. We're going to do a wrapped signature in this case. And we're going to return a piece of XML. So the first thing we do is create a new signed XML object, and we associate the key with the signing key property. And the object is going to keep track of that key, and when we ask for a signature, it will use that key to generate the signature. Pretty straightforward. The next thing we have to do is we have to declare the thing that we want to sign as a data object, and we have to identify it and explain how we want it related to the signature. So in this case, what we're going to say is that it's an embedded object. We're going to embed the signed object inside the XML of the signature. And I have to give it a reference to refer to the signed object from the signature part itself. You'll see it in the output as part of the standard. And so I just give it ID 1 here as a sample. Now I create a hashed reference to that object. And I create a reference object, associate the data object with it, and add it to the overall doc. An individual XML signature can sign any number of XML objects in parallel. You just define all the references to that you want to sign, and then you do one signature operation. This is great if you want to do compound signature over a number of documents without having to do a separate public key operation every time. Finally, we go off and compute the signature over what we've added, and then we return the XML property, which gives us back the XML data structure. Okay. So now what's it look like? I'm going to step you through it because I don't want to scare you all at once. Because those of you who have dealt with any of these signature standards know that there can often be a lot of components. So the first thing we start with is the signature tag. This says that following internal content is part of the XML signature standard. Signature standard always has at least 2 parts. The signed info, which is the stuff being signed, and the signature value. Let's take a look at the signed info first. The first part of the signed info is a declaration of what signature algorithm you're using. Everything in XML DSIG is algorithm independent. There are URLs that define what algorithm, various algorithm types in the standard. That's the current URL defining RSA with a SHA-1 hash signature algorithm in the standard, and so that's what we include here. That's the type of computation we'll do. The next thing we do is we start to include the references for the objects that we're signing. We're only going to have one object here, so we only have one reference clause. And the URI in that reference is the pointer to the object being signed. There it is down there. We wrap the actual stuff that we wanted to sign inside an object tag. We have the IDs match up with the URI, so I know when I look at that reference how to find the object. I use a fragment URI here simply to say that the object that I'm signing is elsewhere in this XML document. If I was signing something on a web page that was accessible to another URL, I'd go off and put the full URL there. I then have a section of transforms. Now, one of the nice things about the XML standard, the digital signature standard, is you can sign sub-pieces of documents without altering the original document. What you do is you declare a transform, such as an XPath or an XSL transform, that you apply to the document before you generate the hash, and that gives you a piece back of it. There's also one transform you always have to apply, which is canonicalization. That's the thing that makes carriage return new lines and new lines all come out to be the same thing and normalizes white space and character sets and things like that. So that's the transform we have here. We then declare how we're going to do our hashing, and it's the SHA-1. We're going to use the SHA-1 hash algorithm. And then I include the actual hash of the object as it came out of the transform, and that's the base 64 encoding of the SHA-1 hash of our little myElement object at the bottom. Now I do my signature, and what I sign is the entire signed info. And there's my signature value, and again, that's just base 64 encoded of the actual signature. You'll notice that there's no certificate references or no key references in this example. You have options to add all of that information in. It gives you additional clauses underneath, between the signature value and the object. You see things called key info, and they identify keys and certificates and PGP stuff and anything else you want that relates to how to find the verifying key. It's communications to the verifier. But you're not required to put any of that in, and that keeps the message size small. And that's basically what it is. If you generate a signed piece of XML, it'll look something like that. We're actually a little bit early, but that's basically the end of this talk. Let's go back and just go back over what we originally presented. I first introduced you to the code access security model, focusing on code access permissions, which is our method of doing authorization checks and walking the stack. We then talked about evidence-based security and our policy system for how we can identify the rights that should be associated with any particular assembly that we load and how flexible that is. And we've shown that and I've pointed out there's a lot of new functionality both for clients and servers, and that you can get all this customization, but you don't have to just to write to our frameworks. And then finally, we've talked about digitally signing XML, and I've given you a little demo of how you can do that using our current classes. I'm sure there's some questions. I guess I should talk about related sessions. These are the sessions that you might also be interested in. ASP Plus talk, which is coming up. The next two, I believe, were already held, but you can go get the notes over in the ComNet. And then the SQL Server talk is tomorrow. If you care more about the XML DSIG standard, there's a URL to the World Wide Web Consortium's homepage for that group, and you can go get that out of the slides. Questions? That ends it. Thank you.
Oh, wait.
Oh. People still want that URL? We can go to questions. I can start taking questions. I'll leave this up. Let's start over here on the right.
Yeah, because the C++ compiler produces non-verifiable code.
Yes.
Even when it's doing managed output, does that imply that the security framework has to treat an application or assembly that has C++ code as completely untrusted?
No, but it does imply that if you load an assembly that is C++ code, you have to be willing to grant it the right to basically avoid verification, or the right to have errors in verification. Now, what that means really deep down is, yes, you are trusting the C++ code. Okay? Once you have allowed unverifiable code to come in, you have the right to scribble over memory.
Right.
And we have no way to protect that. But you can hand out the right to sort of bypass the verification step without handing out the rights to all of the other permissions in the system.
But
So you
sorry.
don't just turn everything off.
Right. Right. But
Okay.
those checks aren't necessarily strong if you're doing C++ code.
They are not as strong, although they will catch a bunch of developer errors.
Right.
And that's part of the reason why we kept the split there.
Okay.
Okay. But you're absolutely right. Once you're running code that you can't guarantee to be type safe, you can escape the bounds of the security system.
Okay.
Okay. Over here.
Way back when we were learning about structured exception handling and so on, they warned us about the terrible, terrible performance burden of walking the stack. How concerned should we be that you're walking the stack?
Well, as concerned as we were about a year ago until we put a whole bunch of perf work into it. But let me tell you some of the things that we've done to make that call a little bit easier. Yes, there's a burden in walking the stack. Our stack walk's actually pretty fast. And there's a couple of things that really impact performance here that work in our favor. First off, because we only grant rights to an assembly, when you have multiple frames on the stack that are from the same assembly, you only end up doing a security check once for that entire group of frames as long as they're all collected together on the stack. Right? Every time you basically do an assembly transition, we end up having to do a security check, but the rest of it, we're not going to take any security cost. Now, there will be a slight stack walk cost, but it's not, I mean, the major part of it is doing the actual security demand check at that point. But we're only looking at the assembly transitions. We also actually do some caching when you load assemblies into the system, where we'll compute the minimum grant set of all of the assemblies that are loaded. And when you do a demand, if you're inside that, we know you're going to pass a stack walk, and we'll bypass the stack walk check. But that's a conservative thing. So there are cases where that will fail, and we'll go do the full stack walk. But we do have a bunch of performance improvements inside the system. And if you play with the bits, I think you'll see that even in the case where you're doing security, a lot of security demands, it's still pretty reasonable.
Thanks.
Over here.
My question is in terms of what context are the assemblies running in? I understand it'll most likely be running in a user mode, but does the assembly at all inherit user permissions or somehow use the user token?
Okay, so if there are ways for the assembly to have access to the user token in the NT sense, and in fact that happens through some of those permission objects, the principal objects in system security principle and the role-based security. So you can do things like impersonate if you have the right to impersonate. But they are running within a particular user context, and we've subdivided inside of that. They do not inherit rights beyond that in the sense that we don't go and translate particular rights out of the NT model if you define something in NT in. Okay, but you do have that user token associated with it, and you can play those same sorts of tricks that you need to.
Okay, thanks.
Doing a server. Next question.
I would assume that you're tied into Active Directory so that I'm able to set rights and privileges at an enterprise level and have it pushed down to all of the clients or users within the environment.
It's not on the current bits that you have in you, okay? The config system that's in the bits you hold in your hand actually is based off a file system sort of config thing. That will be there by V1. I mean, it has to be, otherwise you can't set enterprise policy. Now, let me point out that there's another thing you can do for enterprise policy that might be even more interesting. Because you control the way this stuff plugs in, instead of trying to push new policy files every time to all the clients in your enterprise, you could actually stick a piece of code in that code group that reaches out and acts as a validation server. If you wanted to have tighter control over policy, you could delegate that check back. You'd, of course, take a network hit when you did that, but the advantage would be you could actually control stuff at one central server as opposed to them pushing stuff out. But if you're going to use sort of, the AD group policy, that sort of model, that will be provided, but it's not in the bits you have. Question?
I think I see the answer to this based on the answers to the previous two questions, but how would I go about building a new permission that's granted to an assembly based on who the user is?
Actually, so do you mean based on who the user is in the context of running it, or do you mean
based on roles or groups that the user might belong to?
Okay. So what you do is you'd write a custom code group so that when the assembly got loaded, you'd hang it off the all so that everything looked at it. You'd basically have it match everything, so it had that Boolean function, all return true. And what it would do is it would go out and query the user and build up a permission object to represent whatever rights you wanted and pass that in. That would automatically be OR'd through. So just a custom code group.
Thanks.
Okay. Next question.
Yeah, I was curious about debugging the declarative security checks you talked about at the very beginning. Do those actually generate inline calls on the stack prior to the method being called? So could you step into them and find out where a security problem was?
Well, there's really two phases to it. So there's some verification, there's some validation of the declaration that actually happens at compile time. because the declaration that you write actually gets converted because we have to sort of take a bunch of information and put it onto the declaration, the metadata. So there's some errors that will come back there. The rest of it shows up in the pre-stub of the method that you call. I'm not sure if you will actually see that or not in the current debugger. I'd have to go look. But you should be able to see that exception by the time we reach RTM.
So the intent is for me to be able to actually step through that and see where the
Yeah.
problem may exist.
Yeah, that is the intent.
Okay.
Yeah.
All right, thanks.
Next question.
Most of what you're describing is giving the permission, trying to verify that the code is trusted, and you've already answered a couple questions about how that relates to user permissions. And I guess I just wanted to hear you comment further on if you're using, we have a pretty fair investment in code to handle user permissions using the old APIs, accessing Win32 directly and manipulating ACLs and all that stuff.
Right.
And what do we really need to do in terms of that in this new security framework?
We layer on top of that. So if you're running on top of an NTFS system and you've got the investment in ACLs, that's all still there. Okay. So there is no distinction, or actually, there's basically both levels are present. An assembly in our system has to have file rights to call a managed file class. Now that user context that it's running in still has to have user rights and the user ACL to the native Win32 APIs. The advantage you get is that if you're on a fat file system, where you don't have any of the ACLs and you don't have that security in the file system, you still have what you have from us. But all of the user permissions that come out of your NT accounts and that sort of thing are still present underlying us. And you'll still get errors even if we pass a security check for an assembly, you can still get a failure in the ACL check at the underlying file system.
Okay, thank you.
Okay. What Prarit's saying over here on the right-hand side of the screen is that there's another talk that's been added at 5:30, and I believe it's called the Net Platform Security Services talk, and it will go into some more details of some of the standard services that are available on Win2K and how some of it ties in. Next question, please.
How does this model support application servers where you're running code on behalf of another user? So it's not the process that is the identity, it's the identity of the person that's being called, and your stack may be a virtual stack across multiple machines.
Do you mean across multiple machines or across multiple processes with the user?
I mean multiple machines.
Multiple machines, okay.
Yep.
So that ties in with some of what happens with remoting, okay? So first off, let me tell you what happens once I have to do a context switch or I do a thread switch or a remoting switch, okay? So let me answer that part first, which is that basically we compress the dynamic state of the security permissions on the stack, and that gets added to the top of the next thread. And that same thing is going to happen across a context call. On a remote call in V1, we're not going to have that propagation, okay? So what will happen is if you do a remote procedure call over to the other machine, it's going to start up a security context relative to that. There will be ways in which we can determine identity trust between the two, but we're not propagating the entire stack across multiple machines. There will be too much state there. Now let's talk about what happens in application servers, which is that you're running on behalf of some other user. You may or may not be doing impersonation. I don't know are you doing impersonation?
Yep.
Or not? Okay. So if you're doing impersonation, you are still going to see that user token basically up there on the thread. And you can still, just like I answered the previous gentleman over here, take that information and use it when you're flowing through policy and starting off groups and doing computations. The other thing you can do in an application server situation is you can actually feed a piece of evidence into us that says, by the way, I want you to treat this assembly as coming from this particular user with this particular set of rights. And you write a little bit of custom code on the policy, and it triggers off that and hands stuff back. Okay? Great. Next question.
If I have an object that is use callbacks, so like callback to any type of event handler,
Yep.
Do I need to give that object significant performance to run with I don't know what? Or
Do you mean do you have to give the object permissions in order to do the callback? Or?
when I drop down in the callback on the stack, I will be coming through something like an ActiveX or something
That's
like
right.
that.
That's right. Okay, so the unmanaged frames that are on the stack, right? They're not going to have any managed security necessarily associated with them, and the checks will pass through those because you've stepped outside the bounds of the security system.
Assume you use WinForms or something like that is managed.
Yeah. Okay, so if I'm doing callbacks to there, you'll see the frames on the stack.
Sure, but when I say I have a thing,
right?
What permissions do I give to it? Because I don't know what it's going to call. when I define this assembly that contains
I
the
see.
wind form.
Right. So the wind form itself, I'll tell you what, I got to diagram it out for you. So if I can catch you off to the side, I'll walk you through how it works.
Thanks.
Okay? Next question.
Just one more. When will you or someone else have a book finished about how all this works?
In my copious spare time. I don't have a good answer to that. I know that I've been working with Jeff Richter a lot. You got 3 chapters from his book coming. I know he's going to discuss a lot of the security system later on in that book. I would hope there will be others that will come out from it. He's going to have a lot of examples in there because, well, we've been working through all that sort of stuff. So I know he's going to cover some of it, at least in the final version of that book. I don't know the plans for any of the other books at this time.
Okay, do you know of any other sources for documentation?
Besides what we happen to have in the classes at the moment, no. I mean, it'd be sort of what's in the bits that you have. But I'm sure stuff will be coming. Any other questions? All right, well then thank you very much for your attention.